The solar system is not empty space with planets floating through it. It is a debris field. Billions of rocks orbit the sun on paths that cross, converge, and intersect with Earth's trajectory around the same star. Most of them are too small to matter. Some of them are not. And over the last 2 decades, 10 specific discoveries have exposed just how thin the barrier is between a functioning civilization and a sterilized planet. Number 10. In 2023, the Catalina Sky Survey flagged an object designated 2023DZ2. It was between 40 and 90 meters in diameter. It passed within 175,000 kilometers of Earth, and it was discovered 27 days before closest approach. 27 days of awareness for a rock capable of leveling a metropolitan area. The detection system did not malfunction. It operated exactly as designed. The problem is the design itself. Current survey completeness for near-Earth objects between 50 and 140 meters is approximately 40%. 60% of the objects in that size range have never been observed. That is roughly 15,000 rocks. Their orbits are unknown. Their positions are unknown. Their next Earth-crossing dates are unknown. They exist in the same orbital plane as this planet, subject to the same gravitational forces, and no instrument has ever recorded a single photon from their surfaces. If the detection threshold were lowered to capture objects at twice the current range, 2023 DZ2 would have been identified months earlier. Months translate into response options. 27 days translates into observation only. No deflection, no evacuation at scale, no intervention of any kind. At 27 days, you watch. That is the only option the system provides. And 15,000 untracked objects remain on trajectories that no one can predict because no one has measured them. This is not a gap in knowledge. This is the operational baseline. At current survey rates, reaching 90% completeness for this size range requires at least 2 more decades of continuous observation under optimal conditions. During those decades, every untracked object continues to orbit. Some of them will cross Earth's path. Some will cross it closely. The probability of an undetected 50 to 140 meter impactor entering the atmosphere within any given century is not negligible. It is statistically meaningful. And meaningful probability applied to catastrophic consequence does not wait for the survey to finish. The objects do not pause because the catalog is incomplete. Number 9. On February 15, 2013, a 20-meter asteroid entered Earth's atmosphere above Chelyabinsk, Russia, at 19.16 kilometers per second. No telescope on Earth detected it. No satellite flagged it. No warning system activated. 0 seconds of advance notice. The object detonated at an altitude of 29.7 kilometers, with an airburst energy of 440 kilotons. The shockwave hit the city below at supersonic speed. Over 1,500 people required medical treatment. More than 7,200 buildings sustained damage. The primary injury mechanism was not heat. It was not radiation. It was glass. The overpressure wave shattered windows across a 200 square kilometer area, and thousands of panes launched inward at velocities sufficient to sever tendons, lacerate organs, and embed fragments in bone. The asteroid approached from the sunward side of the sky. Ground-based optical telescopes cannot observe objects embedded in solar glare. This is not a calibration failure. It is a geometric constraint imposed by physics. The sun occupies the exact region of the sky from which the fastest, most dangerous short-warning impactors originate. If Chelyabinsk had arrived 40 meters larger, the airburst altitude drops. The overpressure intensifies. Reinforced concrete fails across a 15-kilometer radius. Hospitals collapse before they can receive patients. Emergency services do not respond to injuries. They become casualties. There is no workaround for this blind spot using ground-based instruments. The geometry is fixed. The sun does not move. The vulnerability is permanent. Every city on the sunward approach corridor exists inside this constraint. A 60-meter object entering from the same vector as Chelyabinsk carries roughly 30 times the energy. The airburst descends to 15 kilometers altitude, where overpressure coupling to the surface intensifies by an order of magnitude. At that energy level, the thermal pulse precedes the shock wave. Exposed skin sustains flash burns before the pressure wave arrives. The sequence is heat, then force, then debris, and the population receives no warning for any of them because the detection system cannot see the approach vector. You are protected from this scenario by probability, not by technology. Probability is not a defense. It is a schedule that has not yet reached your position. Number 8, in July 2019, asteroid 2019 OK passed Earth at a distance of 73,000 kilometers. That is less than 1/5 the distance to the Moon. Its diameter was between 57 and 130 meters. Astronomers detected it less than 24 hours before closest approach. One day, a rock carrying energy equivalent to several hundred megatons of TNT close to within a fraction of the lunar distance, and the entire global observation network delivered a single day of lead time. The orbital geometry was the failure. 2019 OK spent most of its orbit far from the Sun, moving slowly, faint beyond detection thresholds. It only brightened during the final hours of approach, when the angular velocity was highest and the window was smallest. By the time automated algorithms flagged it, the encounter was already underway. A 100-meter impactor striking a coastal city generates a localized tsunami exceeding 10 meters in height. Airburst overpressure collapses wood frame structures across 50 kilometers. Underground infrastructure fractures from ground-coupled shock waves. Water mains rupture. Gas lines ignite. Power transmission fails when towers buckle. If the warning had been 90 days instead of 1, orbital mechanics allow preliminary deflection assessment. Evacuation corridors open. Resource staging becomes possible. At 1 day, none of that exists. The response system requires time that the detection system did not provide. One fails. Both fail. There is no separation between them, and the cascading dependencies extend further than the immediate blast zone. A coastal impact generates electromagnetic pulse effects from the ionized atmospheric channel. Communication satellites in line of sight lose signal integrity. Financial transaction networks operating on sub-second latency halt. Supply chains routing through the affected port system sever. A single impact point produces radiating failure across systems that never physically touch the asteroid or the blast zone. The damage propagates through infrastructure dependencies at the speed of network connectivity, which is faster than the shock wave itself. Number 7. Long-term tracking of small near-Earth asteroids revealed a force that most orbital models had treated as negligible: the Yarkovsky effect. As sunlight heats the surface of a rotating asteroid, the body re-radiates that thermal energy with a slight directional bias determined by its spin axis and rotation rate. The result is a persistent, low-magnitude thrust that pushes the asteroid along its orbital path. For a body like Apophis, this drift is approximately 170 meters per year. That sounds irrelevant. It is not. Over a decade, the displacement compounds to nearly 2 kilometers. Over a century, it rewrites entire encounter geometries, shifting the asteroid's predicted position at a future Earth approach by tens of thousands of kilometers. The Yarkovsky drift depends on surface albedo, thermal inertia, spin state, axis orientation, and shape. For most potentially hazardous asteroids, these parameters are unmeasured. The orbit is known. The force acting on the orbit is not. If the Yarkovsky effect could be precisely quantified for every tracked object, long-range impact probabilities would carry meaningful confidence intervals. Without that data, every prediction published for small asteroids beyond a 50-year horizon carries embedded uncertainty large enough to shift a miss into a hit. Remove this force from the model, and the predictions look clean. Leave it in without measurement, and the predictions look precise, but carry error bars no one discloses. The published numbers appear authoritative. The physics underneath them is incomplete. This connects directly to the gravitational keyhole problem. A keyhole is a narrow corridor in space, sometimes only hundreds of meters wide, that determines whether a future flyby converts into an impact. If the Yarkovsky effect shifts an asteroid's predicted position by even a few kilometers at a future close approach, the question of whether it threads a keyhole or misses it becomes unanswerable. The prediction says safe. The unmeasured force says uncertain, and uncertain applied to a keyhole is indistinguishable from unknown. The entire long-range forecasting system for small asteroids depends on a force it cannot currently measure for most of the objects it tracks. This is not a future problem. It is a present condition. Number 6. In September 2022, NASA's DART spacecraft struck Dimorphos at 6.6 kilometers per second. The orbital period of the 160-meter moonlet shifted by 33 minutes. The mission was declared a success. It was. And inside that success sat a warning that planetary defense planners immediately recognized. The momentum transfer efficiency was approximately 3.6. The ejecta from the impact contributed more to the deflection than the spacecraft itself. The spacecraft was a trigger. The asteroid's own debris was the engine. If Dimorphos had been denser, more cohesive, or less porous, the ejecta contribution drops. The beta factor falls. A successful deflection becomes a marginal one. A marginal one becomes a failure. This means kinetic impactor effectiveness is not a constant. It is target dependent. It depends on grain size, void fraction, internal cohesion, bulk density. Properties that are unknown for the vast majority of potentially hazardous asteroids. The only way to determine whether a kinetic impactor will work against a specific threat is to characterize that threat first with a dedicated reconnaissance mission. Reconnaissance requires years of development, years of transit, and years of proximity observation. If the threat is confirmed with a decade of lead time, those years consume most of the available window. If the threat is confirmed with 5 years of lead time, there is no reconnaissance. There is a guess, and a guess applied to planetary survival is not a strategy. It is a coin toss with civilizational stakes. The DART result also revealed a secondary problem. The impact altered Dimorphos in ways that remain poorly understood months after the event. The moonlet's shape changed. Its rotation state shifted. The debris field persisted longer than models predicted. A deflection attempt is not a clean, controlled input. It is a violent disruption of a body whose response depends on properties that can only be known after the disruption has already occurred. The deflection is irreversible. If the outcome is insufficient, there is no second attempt on the same timeline. One shot, one unknown target, one result that cannot be corrected. Number 5. In 2020, the OSIRIS-REx spacecraft touched the surface of asteroid Bennu. What it found restructured the entire deflection problem. Bennu is 490 meters in diameter. It holds a cumulative impact probability of 1 in 2,700 through the year 2300, with peak risk on September 24th, 2182. Those numbers matter, but the composition matters more. Bennu is a rubble pile. No solid core. No structural integrity. Its interior is a loosely bound aggregate of boulders, gravel, and void space held together by microgravity and weak, cohesive forces. Porosity exceeds 50%. The spacecraft's sampling arms sank 49 centimeters into the surface on contact. The thrusters had to fire immediately to prevent the vehicle from being swallowed by regolith. A kinetic impactor designed to deflect a solid monolithic asteroid transfers momentum through a rigid medium. Strike Bennu, and the energy disperses into rearranging rubble. The crater forms, debris ejects asymmetrically. Internal mass redistributes, but the center of mass does not accelerate cleanly. The asteroid absorbs the force instead of translating it into trajectory change. A gravity tractor requires years of continuous hovering for a body of Bennu's mass. A nuclear standoff detonation has never been tested on any asteroid of any composition. If Bennu requires deflection, the only validated method does not work on its structure, and its structure was completely unknown until a spacecraft physically touched it. This is the deflection problem stated in its most direct form. The method exists, the target defeats it, and Bennu is not an anomaly. Rubble pile structure appears to be the dominant configuration for near-Earth asteroids in this size range. JAXA's Hayabusa 2 mission found a similar structure at asteroid Ryugu. The assumption that asteroids are solid, coherent bodies, an assumption embedded in decades of deflection planning, is contradicted by direct observation at every target visited so far. The deflection models were built for objects that do not appear to exist in the numbers originally assumed. The models work on paper. The asteroids do not match the paper. If Bennu's orbit shifts toward impact geometry in the coming centuries, the response will require a technology that has not been invented, tested, or funded. The timeline for that response begins in 2018. The timeline for developing the technology has not begun. Number 4. In 2004, asteroid 99,942 Apophis reached a Torino scale rating of 4. No object had ever reached that level. Initial calculations placed the probability of Earth impact on April 13, 2029 at 2.7%. A 370-meter body carrying approximately 1,200 megatons of kinetic energy had a statistically meaningful chance of striking this planet. The mechanism was gravitational. Apophis crosses Earth's orbit twice per cycle. During the 2029 flyby, it will pass closer than geostationary communication satellites. That encounter is locked into orbital mechanics. It will happen. During that flyby, if the asteroid passes through a gravitational keyhole roughly 600 meters wide, Earth's gravity bends its trajectory into a resonant return orbit. 7 years later, it impacts. One flyby, one corridor, one outcome. Subsequent observations eliminated the 2029 keyhole risk specifically, but the structural principle was not eliminated. Gravitational keyholes exist for dozens of tracked asteroids. Each close approach rewrites the next. A harmless flyby becomes a setup for a lethal return. The conversion requires no additional force. Gravity alone is sufficient. Remove the flyby and the threat vanishes. But the flyby is orbital law. It cannot be removed. It can only be survived. And survival depends on which 600-meter window the asteroid happens to thread. That is the margin. 40 minutes of gravitational interaction determining whether a civilization continues or does not. A 1,200 megaton surface. Impact from a 370-meter asteroid excavates a crater roughly 4 kilometers wide. The ejecta blanket buries everything within a 20-kilometer radius under meters of debris. The atmospheric shock wave strips structures from foundations across a 100-kilometer radius. If the impact occurs in an ocean basin, the displaced water column generates a tsunami propagating outward at 800 kilometers per hour with initial wave heights exceeding 30 meters. Coastal cities within 1,000 kilometers receive less than 2 hours of warning before inundation. And this entire consequence chain pivots on which 600 meters of space are rock threads during a 40-minute window in 2029. The keyhole concept is not unique to Apophis. Dozens of tracked near-Earth asteroids possess identified keyholes for future encounters. Each close approach is a filter. Pass through cleanly, and the next orbit is benign. Thread the keyhole, and the next orbit terminates at the surface. The system does not escalate gradually. It switches states. Number 3. The ENIO Surveyor mission is the primary next-generation space-based detection instrument for near-Earth objects. It is designed to operate in infrared from a Sun-Earth Lagrange point, specifically to close the solar blind spot that Chelyabinsk exposed and that ground-based telescopes cannot address. Its launch has been delayed multiple times. Every year of delay is a year the detection gap persists at its current width. Every year the gap persists is a year during which an undetected object between 50 and 300 meters can approach Earth without activating any warning system operated by any nation on the planet. The entire planetary defense architecture rests on a sequence: detect, track, characterize, deflect. If detection fails, the sequence terminates at step 1. Tracking cannot begin on an object that has not been found. Characterization cannot begin on an object that has not been tracked. Deflection cannot be planned for an object that has not been characterized. The chain is serial. There is no parallel path. There is no redundancy. One failure at the front end collapses every capability downstream. And right now, the front end is a collection of ground-based telescopes that cannot see sunward, one aging infrared satellite, and a next-generation replacement that has not yet left the ground. This is the system. There is no backup system. Number 2, in 2017, the first confirmed interstellar object passed through the inner solar system. Designated 1I/Oumuamua, it was detected after it had already passed closest approach and was outbound. Its velocity exceeded solar escape speed. It originated outside the solar system entirely. The threat implication is not about Oumuamua specifically. It is about the category. An interstellar impactor travels at velocities of 26 to 70 kilometers per second. Kinetic energy scales with the square of velocity. A 200-meter interstellar object carries 4 to 9 times the energy of a same-sized near-Earth asteroid. Detection lead times collapse because the object crosses the inner solar system in weeks. Deflection is physically impossible. No propulsion system exists that can generate the required delta V in the available window. Fragmentation produces a debris field that strikes the same target zone. There is no intercept. There is no redirect. The only response is ground-level evacuation, and the warning window may be days for a strike zone measured in hundreds of kilometers. Current models estimate 1 to 10 interstellar objects transit within Earth's orbital radius every year. They are not rare, they are undetectable until final approach, and undeflectable after detection. The entire planetary defense framework assumes threats that originate within the solar system and travel at solar system velocities. Interstellar objects violate both assumptions simultaneously. This is a failure mode that exists outside the design envelope of every mitigation strategy currently funded, proposed, or theorized. There is no recovery path. Every deflection strategy in the current planetary defense portfolio requires 2 things: sufficient lead time and manageable relative velocity. Interstellar objects eliminate both. The lead time compresses below any mission development cycle. The velocity exceeds any propulsive capability. These are not engineering limitations that can be solved with more funding or faster development. They are physical constraints imposed by the energy scales involved. A spacecraft launched to intercept an inbound interstellar object at 50 kilometers per second would need to match that velocity to rendezvous, or exceed it to arrive first. No chemical, nuclear thermal, or ion propulsion system in existence or in development can produce those velocities on the required timeline. The object arrives, it strikes. The physics is non-negotiable. Number 1, long-period comets originate in the Oort cloud, a spherical shell of icy bodies extending from 2,000 to 100,000 astronomical units from the Sun. Their orbital periods exceed 200 years. Many exceed 10,000. Some are making their first passage through the inner solar system since the formation of the star they orbit. They are not tracked between apparitions because they spend millennia at distances no telescope can reach. When gravitational perturbations from passing stars or galactic tidal forces dislodge them, they fall inward. Solar gravity accelerates them to 40 to 60 kilometers per second at Earth-crossing distance. A 5-kilometer long period comet striking Earth delivers energy in the hundreds of millions of megatons. The atmospheric shockwave ignites forests across a continent. Ejecta re-enters the atmosphere globally and raises surface temperatures by hundreds of degrees for hours. Sunlight is blocked within days as particulate loading saturates the stratosphere. Photosynthesis ceases. Agricultural systems collapse within a single growing season. Grain reserves, calculated for logistical disruption, are not sized for global photosynthetic shutdown. Livestock populations collapse when feed supplies terminate. Freshwater systems destabilize as particulate fallout contaminates surface reservoirs. Ocean thermal circulation fractures as surface temperatures drop and salinity gradients shift. The cascade moves from atmosphere to biosphere to civilization in a sequence that no infrastructure on Earth is built to interrupt. The detection window for a new long-period comet on an Earth intercept trajectory is 6 months to 2 years. No deflection technology can alter the trajectory of a multi-kilometer cometary nucleus in that window. The mass is too large. The velocity is too high. The available force is too small. The Chicxulub impactor that ended the Cretaceous period and eliminated 75% of all species on Earth was likely an object in this category. That was 66 million years ago. The Oort cloud has not emptied since then. It contains an estimated 1 to 2 trillion objects larger than 1 kilometer. Gravitational perturbations from passing stars, molecular clouds, and the galactic tidal field continuously dislodge members of this reservoir and send them falling inward. The supply is functionally inexhaustible on any timescale relevant to human civilization. The rate of infall is low but non-zero, and non-zero, applied across geological time, converges on certainty. The next one is already in motion, displaced from its orbit years or decades ago, accelerating silently toward the inner solar system on a trajectory that no instrument is monitoring. There is no early warning network for the Oort cloud. There is no detection perimeter at 10,000 astronomical units. There is no system designed to stop it. There is no system that could stop it. The atmosphere you are breathing persists because nothing large enough has struck this planet in 66 million years. That is not protection. That is not design. That is a duration between events. And durations end.